All right, let's look at some architectural aspects of the songline processor. And I'm going to work with four-sided cells because that's a smaller jump from the cell matrix that we're used to with four-sided cells. But we're going to talk about three-sided cells after this because that's the version that we've actually implemented in simulation. But here's a simple setup. So this is cell 0, 0, this is cell 1, 0, north, south, west, east. And I'm only going to pay attention to the data lines. There is a set of C lines as well, just as with the cell matrix, but we're going to ignore those for the time being for the next few videos. We're just going to talk about D-mode processing. So there's a function inside each of these that takes 4 inputs and generates 4 outputs. And we're going to explore what we can do with that. So for example, this northern output here we could write as F0, 0, north, and it's a function of some north, south, west, east inputs. So let's see what we can do with this, and let me clean this up. Again, get rid of the arrows and intercell connections, and let's start with the simplest of all circuits, which is an input coming here, an output coming here, and we simply connect these. So F0, 0 north equals west. It's an identity function. Most fundamental behavior, and this is a wire that can take in a voltage level from 0 to 5 and produce a voltage level from 0 to 5. Now if we envision a block in here which does multiplication, this would become an amplifier. It would take an input and it would produce an output whose value is 1,000 times the input. And we could do that as follows. We could say the function's output to the north is equal to, and let's do this with 2 cases, it could be 1,000 times the west if west is less than or equal to 0.001. It could be 1 if west is bigger than a millivolt. And so this is a clipping amplifier. Any voltage from 0 to a millivolt will get amplified 1000x. And anything a millivolt or larger will simply produce a 1 volt output. So that's an amplifier. Now a slightly more useful circuit might be a variable gain amplifier. So we can build another function down here. So we'll take the western input to this cell as the gain, and we'll take a northern output into here, and this is just our wire. So let me add indices here. That's cell 0, 0. This is cell 1, 0. So now the function of cell 0, 0 to the north is equal to the following. It's equal to, well, we'll use the gain input to specify how much we want to amplify the input by. So it can be the input times 200, sorry, input is from the west. West times 200 times south, if west is less than or equal to 0.001, and it could just be 1 if west is bigger than 0.001. So now we can control the gain. If we put this at 0 volts, it's not amplifying at all. If we put it at 5 volts, it's doing 1000x amplification. And we could make this function a little more reasonable by saying, instead of limiting this to the value of W, we could say if W times 200 times S is less than or equal to 1, and it could just be 1 if W times 200 times S is greater than 1. So now if we set our gain to be 2x, we can go all the way up to a half volt input. So these are well-defined mathematical functions, in this case function of 2 input variables producing a single output. This is still function 1, 0 north equals west. That's our wire. And there's a variable gain amplifier. All right, what else can we do with this? Picture the following circuit. we have some input coming to the west, and we have another cell over here, and this cell basically takes an input value and echoes it back. So this is just function to the west equals west. And this cell over here is going to do the following: function east, so the output coming here is equal to the value coming in plus in minus 2.5 over 1,000. So we have our input come in, we subtract 2.5, we take that output, we divide by 1,000, we take that and we sum it with this, and we produce an output back to the neighbor. And we're also going to take this and send it to the north. So the same thing. What is this circuit going to do? Well, if our input is 2.5 volts, when we subtract 2.5 we get 0. This is going to be output to the east is just equal to the east, and the output to the north will be the same thing. So whatever voltage level this is producing as an output will get sent back in, and that value will persist. So suppose that originally, here's our input, here's our output. So suppose that originally our input is 2.5 volts, and let's just suppose our output is 0 volts. Now what happens is I increase the input a little bit, so I bring the input up to, well, maybe more than a little bit. Let's just bring the input up to some value like 4. So now input minus 2.5 is positive. It's 1.5 divided by 1,000, 1.5 millivolts. Whatever voltage is coming from this cell will get increased by 1.5 millivolts and sent back in here. And when it comes back in here, it'll come back out again and get increased by another 1.5 millivolts and go back in and come out and get increased again. And so this output is going to begin to increase as long as the input is above 2.5 volts. And the time factor for this, the dt, the delta t, is simply how quickly the circuitry can take an input and generate an output, how quickly it can feed it back, get it through this circuitry, and send it back into the reflector. So at some point, if our input comes back to 0, and this happens to be putting out 3 volts at that time, well, our input is 2.5, so minus 2.5 is 0, and we don't add anything, and this output voltage is now stable, so our output is flat. And now if our input goes to what we take as negative, something less than 2.5 volts, the output is going to begin to drop. And when we bring the input back up to 2.5, the output will stabilize. So what is this doing mathematically? It's summing the inputs across time. This is integration. So we can do an integration of an incoming signal by using a circuit like this. It's 2 cells. It's a relatively simple pair of functions, and that sums our inputs across time. So we can do half of calculus, and we can do the other half pretty easily as well. So differentiation is simply looking at inputs and seeing how they change over time. So here's an input value, and we can take this and send it to a cell down here, and we could send that to a cell below it, and that could reflect, and that could come out. And now we have a delayed version of this input. And if we take the western value and the southern value, let's call this A, B, and take their difference and send that out, we've got differentiation. Because this output to the north will be the input's current value minus its value from a little while ago. So it's f of x plus delta x minus f of x divided by delta t. So this differentiates, and if your input is flat, then A and the delayed version of A will be the same and your output will be 0. And as your input begins to increase, A will begin to be larger than B, and this output will suddenly jump up. And as long as your increase is at a constant rate, your output will be constant. And when your input stops increasing, your output will drop down to 0. So differencing pairs of inputs where the second input is a delayed version of the first input. So that's just a small selection of circuits that we could implement using this architecture. Multiplication, variable gain amplification, integration, differentiation. Let's look at some more versions of this. But I also want to switch to the three-sided cell because that's the version that we've implemented, and we'll explain why that is, and then we'll see a circuit using a three-sided approach in the next video.